Welcome, everyone. We're just going to wait a couple seconds and let everybody get in. Looks like the attendees are filling up. All right. Well, hello, everyone, and welcome to today's webinar, How to Fill the Void, Mitigation of Voiding for Bottom Terminated Components. My name is Jeremy Glanzer. I'll be your moderator today. I work on the marketing team here at FCT Solder, Blue Ring Stencils, and A Laser. I'm excited to be hosting this today. I'm pleased to announce and introduce today's speakers, Tony Lentz and Greg Smith. Tony is a field application engineer at FCT Solder, and Greg is our manager of stencil technology. And they have worked on this presentation together, which was originally presented at Apex 2020. Tony and Greg are very highly involved in the technical conference community, so be on the lookout for their continued work. Before we begin the presentation, I just have a couple of housekeeping items to cover. First of all, today's webinar will be recorded and will be available on demand after the session. Next, we'd love to hear from you guys during the presentation. So if you have any questions for our speakers, please feel free to send it through the Ask a Questions tab. And then after the presentation, we'll go through and try to answer some of those for you. If we don't get to your question during the webinar today, we will be sure to follow up with you afterwards. And always, you can email or contact us through the website or contact Tony and Greg personally with any questions. So without further ado, we will begin. Sorry, guys, we're going to start that again.
Hello, my name is Tony Lentz with FCT Assembly. This paper is titled Fill the Void 5, Mitigation of Voiding for Bottom Terminated Components. It was originally presented at IPC Apex Expo 2020.
And my name is Greg Smith, the co-author of this work.
First, we'll talk a little bit about voiding. What is all the fuss about? Why are we all discussing voiding and writing papers on voiding in solder joints? Why is it important to us? And we'll talk a little bit about the causes of voiding, what are the potential factors that can contribute to that, and what did we specifically test in this work. Then we'll go into some detail on the methodology or the way we set up the experiment. Then I have lots of results to share with you. The results are broken out by stencil thickness, area of coverage, by component size, component type, and by the input-output pad toe adder, or the stencil design that we used to make these experiments. And then at the end, I'll have some conclusions, and we'll give recommendations on how to mitigate voiding on your own circuit boards. So when we talk about voiding, what is all the fuss about? So voids are very large, or there's a high void area, or there's a lot of voids concentrated on a plane in the solder joint, like between the component and the solder joint or at the board pad interface. Then that can lead to mechanical failure or cracking in the solder joint, like what is shown in this BGA cross-sectional picture on the left. You can see a very large void in the center of that BGA sphere, and that led to cracking in the solder joint.
Voids can also lead to an overheating failure in the components. It's especially true for bottom-terminated components that are using a central thermal pad to transfer heat away from the component. If the void area is too high, it acts as an insulator, and it can reduce the heat transfer out of that component. LED components are really susceptible to this. If there are large areas of voiding in the solder joints of the LEDs, they can burn out or fail prematurely.
Then the last problem that I've heard about with voiding is electrical signal degradation or noise in the circuit. And that's especially a problem for RF circuit designs. The bottom line is voids are hard to rework. Once a void exists in a solder joint, the only thing you can really do is try to melt that solder joint and resolder it, but it's very difficult to totally eliminate voids that way. I've seen voids reappear under those conditions. So the best option is to try to limit the amount of voiding that's going to form, reduce the void area through mitigation factors up front. So here are some of the causes that can contribute to voiding. This is a pretty small fishbone diagram with cause and effect of different aspects of the SMT process. In terms of print or dispense, the volume of solder paste that's printed, or more specifically the stencil design of both the thermal pad and the perimeter pads, is important in terms of voiding for QFN type components. Reflow profile certainly has an effect on voiding. Adjusting the reflow profile and tuning it to make it work with the solder paste and the circuit board can have some impact. It can minimize voiding to a certain extent. And the solder paste itself certainly plays a role in voiding. Those are the three major areas we're studying in this particular work. In prior work, we've studied several of these other factors and in relation to voiding and how they impact voiding.
So what can we change in our process to get rid of voiding? The stuff that's easy to change is shown on the left, and the stuff that's more difficult to change is shown on the right. One of the easy to change things would be your solder paste. You could get a sample of paste from your supplier within a few days or possibly a week. Some solder pastes have a lower potential for voiding than others, so that change alone may help reduce voiding. Another thing you can change would be the stencil design. Modify the design with your stencil supplier and you could have it within 1 or 2 days, and that may have an impact as well on voiding. Finally, changing the reflow profile is easy to do also. Reflow profile modifications can be done within an hour or two, and that may also have an impact on voiding.
The stuff that's harder to change but also has a big effect on voiding is the board design itself and the components that you use. For example, using a bottom terminated component like a QFN rather than a leaded component like a QFP is going to lend itself to higher voiding levels. Voids tend to congregate in that solder joint, and if it's a gas bubble type void, it's going to rise up to that flat bottom of a bottom terminated component and then not be able to move much. It's not going to migrate. Whereas with a component that has a higher standoff, the solder joints don't have a hard top on them, and so the voids can make it their way to the top surface of that solder joint and then burst out like a bubble, and then the solder joint can collapse and coalesce and have much lower voiding because of that. V and pad designs also contribute to voiding. There's a lot of things with board design and components that can create situations where voiding is prevalent. The reflow equipment that you use itself can have a large impact on voiding. If you can use vacuum in your reflow process, that's one sure way of reducing voiding regardless of all these other factors. But it's not easy to just go buy a piece of reflow equipment with vacuum and throw it into your process. But if you are looking to buy new reflow equipment, I would recommend considering something with vacuum or something with ultrasonic agitation, something that has some technology in it to help reduce voiding potential. And then the surface finish of the circuit board itself, it's kind of part of board design and components. I separated it out here because it does have an impact on voiding. And recently I've written a couple of papers studying that itself. I looked at different surface finishes and what impact they had on solder paste performance, just generally speaking. But one of the things I looked at specifically was voiding potential based on surface finish. And there's a big difference from one surface finish to the next. So if you have the ability to change surface finish, you should certainly consider that. If you don't, I understand sometimes you're given surface finishes that you don't have any control over which one is given to you, and you just have to make it work. the papers that I was talking about in terms of surface finish, discuss that a little bit and give recommendations on how to deal with different surface finishes. So here's the methodology, or how we set up our experiment. On the left is the circuit board design that we used, and on the right is the stencil design that went along with that. We're basically using the lower half of this circuit board, the QFN 10s, which are circled, and the QFN 7s and the QFN 4s. Those are 10 millimeter, 7 millimeter, and 4 millimeter body components. We are not using the columns in the center here. Those are QFN 9 millimeters. And then the circuit board laminate material was standard FR4, 0.062 inches thick with 1 ounce copper. It's an printed and etched type circuit design with standard semi-matte green solder mask and an ENIG surface finish.
The stencil design we used on the right was varied widely for each one of these components. Each component has 2 columns. The QFN 10, for example, has 70% coverage in the left column and 60% coverage on the thermal pad in the right column. The rows have different I/O aperture lengths. The first row is 1-to-1 with the copper pad, so the printed solder paste brick will be the same size as the copper land pad. The second row has 5 mils added to the toe or the outside of the pad away from the center of the component. The third row has 10 mils added to the toe, and the fourth row has 20 mils added to the toe or the outside of the pad. The theory here is that by adding solder paste to the toe, when these pads reflow, the paste will pull into the copper pad. These pads will become slightly taller and lift the entire component. This lift will then raise the center thermal area of the component slightly, creating a gap to allow gases and volatiles to escape during reflow. So we use these stencil designs along with different component sizes to better understand how stencil design could influence overall voiding. In prior work, we've definitely seen the impact of overall thermal pad paste coverage on voiding behavior.
Here's a full breakdown on the stencil design in case you're interested. We've got 3 components, QFN 10, QFN 7, QFN 4 on the left, and then the thermal paste areas, the number of panes we use, the web width, the brick size itself. Then on the perimeter pads are shown on the right side of this table. All the perimeter pad widths are shown, and then after that it's the length for the 1-to-1 pad, the length plus 5 mils, plus 10 mils, and plus 20 mils. So that's a breakdown on how we design these stencils. 2 stencil thicknesses were made. We made a 4 mil thick and a 5 mil thick stencil with the same exact designs. So we varied the volume again by 20% roughly by changing the stencil thickness from 4 to 5 mils. Well, from 5 to 4. 5 was the standard stencil thickness, reduced it to 4. And so we have a combination of varying the area of coverage on the thermal pad, the stencil thickness, and then the perimeter or I/O pad lengths of print. We tested 5 different reflow profiles with this. The first reflow profile is a linear ramp to spike, and you can see the measured parameters shown here. The slope, the soak time, the reflow time, the peak temp, and the total length of the profile. We made a short version of that linear ramp, and the short version is about 3.9 minutes long versus about 4.5 minutes long for the linear ramp to spike. So we took about 30 seconds off the profile length. Then we made that same short profile, but we added a soak to it. So we added about 30 seconds in that soak zone of 150 to 200 C, and the overall length was increased by that amount of time. And then we made a long version of the linear ramp profile. So this is a linear ramp to peak, just longer. So the length of the profile on the very right is about 5.5 minutes versus 4.5 minutes. So we bumped it up by a full minute. And then we took that long profile and added a soak to it. So we added again about 30 seconds in the soak temperature range. And then the length was increased roughly by that same 30 seconds. After testing all 5 of these profiles in preliminary experiments, we measured voiding on the circuit boards, and we found that overall for this design and for the solder paste that we chose, this linear ramp to spike profile gave the lowest overall voiding, so it's highlighted in green. And that's the profile that we used to continue this work for all the other experiments. Here's a plot of that linear ramp to peak profile that we chose. Again, that was the lowest overall voiding with the solder paste that we used. Now, if you use a different solder paste, I would recommend doing something similar, testing several different profiles based on your solder paste supplier's recommendations. One of those profiles is probably going to give you lower voiding than the others. Or in some cases, maybe 2 or 3 profiles all give similar voiding results, and maybe 1 or 2 give higher voiding results. It just depends on the solder paste and the circuit board design.
The statistics that we're going to use when discussing voiding will be similar to what's shown here. We'll use box plot diagrams like this to analyze the data. In this example, on the y-axis, we have a void area percentage. So the area of the solder joint that is a void versus the total solder joint area is shown here. Then we break apart the variables that we're studying on the x-axis. In this case, it is paste area coverage of 60% versus 70%. We also like to use Tukey-Kramer analysis, which is an honest significant difference test to analyze data in this paper. The analysis is run with a 95% confidence level, meaning we're 95% sure that the data sets are statistically different or not based on this test. Also, we like to use the connecting letters report this analysis generates, which is shown at the bottom of the report. The report assigns different letter codes to each data set. In this example, the 70% paste is identified with letter code A, and the 60% coverage is identified with letter B. Since each percentage has a single unique letter assigned, we know that these data sets are significantly different from each other, which means they give significantly different levels of voiding. So in this particular example, 70% coverage of paste gave a higher percentage of voiding than 60% coverage.
The process that we used to do this is shown here. We printed the solder paste, placed components, and refilled the circuit boards. Then we took pictures of the solder joints, and then we measured voiding, and then we repeated that cycle for 20 boards for each of both stencils. So we made a total of 40 circuit boards and analyzed the data out of that. The data included inspection of wetting or solder fillet formation. We wanted to make sure those perimeter pads were making proper IPC specified solder joints. We also looked at bridging to see if there was any bridging occurring or any skew of the components. And then we measured voiding with our X-ray system. We looked at the area of the voiding and then the size of the largest void. Here are the results.
Here are the pictures of the solder joints of the QFN10 components, and the pictures are organized from left to right. You've got 60% and 70% coverage with 0 overprint to the toe on the upper left, to 60% and 70% coverage with a 20 mil toe adder on the lower right. As you can see, the solder joints are not really visible with the 0 toe adder, and on the 5 mil toe adder, you start to see a little more flux and solder on the outside of the component. With the 10 and 20 mil overprint to the toe, it's much easier to see the solder beading to the side and protruding somewhat to the outside of the lead areas. Actually, looking at the 20 mil overprint, you can see a significant amount of paste to the outside of the part. Although on most bottom terminated devices, you don't actually get wetting at the side of the lead, we can see the solder beading significantly on the 10 and 20 mil overprint. The solder joints technically meet IPC criteria, although many folks may not want to see the results shown on the 70% volume coverage and 20 mil overprint in that bottom right picture. These results would meet IPC acceptance criteria if there's no bridging, no skew, and spacing isn't violated. And there was no skew or bridging noted on any of the printed circuit boards that we placed parts on and then reflowed.
Here is the first set of voiding data. This is voiding broken out by stencil thickness. So on the very left, we have overall just all the data lumped together, split apart by stencil thickness. Then in the center, we looked at stencil thickness for the 60% area of coverage and then stencil thickness for the 70% area of coverage. So on the left, we have 4 versus 5 mils. There's a significant difference in voiding there. The 4 mil thick stencil gave higher voiding overall than the 5. In the center, 60% area of coverage, the same trend is shown. The 4 mil thick stencil gave higher voiding than the 5. And then on the right, 70% area of coverage, the 2 stencil thicknesses had equivalent levels of voiding. And that's basically due to you have enough coverage with 70% area to minimize the amount of voiding, so the stencil thickness didn't make enough difference there. Generally speaking, increasing either thickness or area of coverage will reduce voiding in the thermal pad solder joint.
Here's the voiding broken out by area of coverage separated by the different stencil thicknesses. The 4 mil thick stencil data is on the left and the 5 mil thick stencil data is on the right. This is really a different way to look at the same data we just looked at previously, but we just sliced it up a little differently. If you look at the chart on the left, 60 versus 70% coverages gave statistically the same void percentage since both have the letter code A, so there's no statistical difference. For the 5 mil thick stencil, the 70% area coverage actually showed higher voiding than the 60% area coverage. Although our previous work showed increasing coverage area reduced voiding percentage, this data does not agree.
Here's a breakdown of voiding by component size. We used 3 sizes of QFNs, a 10 millimeter QFN, a 7 millimeter QFN, and a 4 millimeter QFN. And you can see on the left, there are different void levels for each one of these component sizes, and they are significantly different. The small QFN4 gave the highest overall voiding, while the QFN7 gave a moderate level of voiding, and the QFN10 gave the lowest overall level of voiding. And the pictures on the right are perfect examples of that. You've got a QFN10, which has 7% void area in that image, versus 15% void area for the QFN7, and that small QFN4 has 23% void area in that particular image. This is pretty consistent throughout our tests. And this is something we've seen before in prior work. Component size definitely has an impact on voiding.
Here's voiding broken out by the toe adder on the stencil, and we also broke this out by the component size. The QFN4 is on the left, QFN7 in the center, and QFN10 is on the right. The toe adder size is 0 toe adder, 5 mil toe adder, 10 mil, and 20 mil toe adder. All 3 of these charts show the same exact trend. Increasing the length of the toe adder dramatically reduced voiding on the component thermal pad. That is statistically significant on all of these components. You can see for 0 toe adder, the voiding is higher than 10 or 20 on all of these examples. So simply by increasing the overprint on the toe of the I/O pads on the QFNs, you can reduce your voiding level. These results leads itself to support our theory that overprinting the toe of the I/O pads causes the part to lift as the solder goes liquid and pulls to the copper pad. This lifting allows space for volatiles to escape during the reflow process, and then as the solder freezes, the part draws back down, resulting in lower void percentages. This is something that was also previously presented by AIM, and they had very similar results.
Here's some example pictures of voiding by toe adder, and the data broken out a little more refined. We've broken this data out by both stencil thickness and area of coverage and toe adder. So you've got all 3 stencil designs on this one chart. So you can see we've got 4 mil on the left column, 5 mil thick stencil on the right column, 60% area of coverage at the top, 70% area of coverage at the bottom. And then that's broken out by toe adder from 0 to 20 mils. Again, you got the same trends from 0 to 5 to 10 to 20. The voiding drops in every one of these. So toe adder changes affect voiding regardless of paste area or stencil thickness. And these pictures on the left are a nice example of that. You've got the QFN7 with plus 5 toe, plus 10 toe, and plus 20 toe from left to right. And you can see how much the voiding dropped from 23% to 15% to 5% just by changing the toe adder on the design. And those are all for the same area of coverage and same stencil thickness.
So here's a summary of all the voiding results of all the combinations that we ran. I don't expect you to be able to read this chart after all. I can barely read it after spending time trying. However, if you look at the right, what I want to point out are general trends of the data. The connecting letters report is ranked from highest void percent to lowest, and every combination is represented. At the top of this chart, the highest voiding levels are produced by the small QFN sizes, the 4 mil thick stencil, and 0 and 5 mil toe overprint to the I/O pads. At the bottom of the chart, we see the larger QFNs, the 5 mil thick stencils, and plus 10 to plus 20 mil toe adders to the I/O pads. Those all gave the lowest voiding percentages in the study.
So here are the conclusions we can draw from this. In conclusion, the linear ramp to spike profile produced the lowest voiding with the solder paste that we chose to use. That may not be true for other solder pastes. So again, I would recommend that you run different profiles with the solder paste you use in order to minimize voiding for that particular product. Increasing the stencil foil thickness from 4 mils to 5 mils had a significant effect of reducing voiding. So if you have the ability to do that, I would recommend it. Increasing area of coverage from 60 to 70% did not have a significant effect in all cases. Sometimes 70% void area gave higher voiding than 60, sometimes 60 gave higher voiding. So it's not a dramatic of enough change to really impact voiding, or at least we saw mixed results. Overall voiding did decrease as the QFN component body size went up. And I know many of you don't have the choice on what type of components you use, but if you do, if you can use larger QFNs, it seems to be helpful. And then overprinting the IO toe on the perimeter pads definitely had an impact. That reduced void area regardless of all the other factors. It overrode all the other factors. So here are recommendations based on these conclusions. We recommend choosing a low voiding solder paste and fine-tune the appropriate refill profile to go with that solder paste. Increasing the stencil thickness or the area of coverage tends to help. Now, I just got done saying that 60 versus 70% area of coverage did not have a dramatic effect in our study. In fact, it gave mixed results. But in prior work, we varied the area of coverage from 50 to 60, 70, and 80% area of coverage. And there's definitely a trend there. 50% area of coverage was too low, and it gave much higher voiding than 80% area of coverage. But with that being said, as you go up to higher areas of coverage, if you go up to 80% area of coverage on a thermal pad, you can have a problem with float or skew of those QFNs, so you got to be careful with that. And then I definitely recommend overprinting to the toe of the QFN IO pads. If you do that, you're going to reduce voiding, and that's going to override some of these other factors. Thank you for your time and your attention and for listening to this presentation. If you have any questions, please email us at the email addresses shown here. We'd be happy to talk with you. Thank you. Have a great day.
Thanks, Tony and Greg. Now I just want to open up the floor to some questions. We've got a couple that have come in right now. So for Tony and Greg, what about voiding for components besides QFNs? Do other BTCs like LEDs and DPACs follow the same voiding trends? Tony and Greg, I'll open it up.
Yeah, I'll tackle that question. So we have run some studies with LEDs and DPACs. At least I've seen studies with our customers who've run those type of tests with our products. And there's definitely a trend there as well. Use of low voiding solder pastes and fine-tuning the profiles have an effect with those components, just like with QFNs. But in that case, those QFNs don't necessarily have the perimeter pads like we do with QFNs. And so we couldn't test that particular theory on lengthening the IO toe print to see what effect that would have. But increasing the area of coverage does seem to help with LEDs and DPACs, up to the point where if you have too much area of coverage or too much solder paste volume, you can get float or skew. And so you have to be careful to balance that out and make sure you're not causing one problem by solving another problem. But certainly increasing area of coverage or stencil thickness can help reduce voiding for those components as well.
Thanks,
Yeah,
Tony.
I agree. I was going to chime in on that. The key with LEDs, from what I've seen, is you, for one, you can't just print those pads one-to-one, especially like if the LED has one large pad on one side and a smaller pad on the other. If you just print those one-to-one with copper, then almost always you'll get some float or skew or pulling from the part of try to center on the large pad or the small pad. So you have to be able to reduce the volume of paste applied to those pads enough to not get that pull or skew, but get enough volume to minimize voids. So that's a little bit of a trick in that. I think we've kind of got a pretty good rule set now for most LEDs.
Awesome. Thanks, Greg. We've got a question from Pedro Martinez. Would this method approach work on LGA pads?
I'll take that, Tony. I've not actually tried this on LGAs.
I know I would be a little concerned with some LGAs that I've seen, and I'm not an expert on all the LGAs out there, but where if we overprinted, we want to make sure that we're not creating solder balls or other issues. We don't typically see that with bottom terminated components like a QFN in this case, but that would be my only concern, would be to not cause any other issues by doing that. But no, we did not do that in this particular paper on LGAs.
Okay. We have a question, and I think Tony had touched on it briefly. How do solder paste affect voiding? Would the use of an ultra low voiding solder paste reduce these voiding levels?
Yeah, certainly. I'll take that question. Solder pastes certainly do affect voiding. I've seen cases where changing solder paste had a dramatic effect at reducing voiding. And I've also seen other cases where switching solder pastes kind of gave the same level of voiding. It just depends on which factors are the strongest in that particular assembly. For example, with QFN and other thermal pads, via and pad designs are becoming more common. And anytime you put a via hole in a pad, you're creating an opportunity for voiding to occur for two reasons. Solder paste will flow down into the via pad. If it's printed directly over that hole, it'll flow down into that hole and therefore drain solder away from the solder joint, which leads to the opportunity for more gaps in that solder joint, which by definition are voids. And the other thing can happen, you can also get gases coming up out of that via hole into the solder joint, creating gas bubble type voiding. And so VM pad designs are tricky, and sometimes switching solder pastes with those won't necessarily have an effect.
Okay.
But in other cases, you can switch solder pastes and that can have a dramatic effect. So it's worth a try. If I were running a process and struggling with voiding and I tried reflow profile changes and stencil designs and nothing was working, I would try switching solder paste. It's worth a shot.
Okay. We got a question in from Jerry as well. Is the toe adder going to work with a 0.4 millimeter pitch, 128 IDQFP with 6.5 millimeter times 6.5 millimeter thermal pad? The standoff is from 2 to 6 mil. For the numbers, Tony, you can see that in your Q&A from Jerry.
Greg, do you want to tackle that question?
Yes, I'll attempt to. Hey, so the first answer is, Jerry, we didn't try this approach with a 0.4 millimeter pitch component. And so it would be hard to know until we actually did some experiments with it. But I would think that it would help. I wouldn't be afraid to. I know that if we're going to start looking at adding length or more solder paste to the toe of the perimeters of the IO pads, one thing that we have to be careful of is to make sure there are no other copper areas, that we're going to short to, right? So we've got to make sure as we start to lengthen those apertures and overprint that there's no open vias, around the perimeter of the component or no other components very close. So my gut is that would still help reduce voiding on that 0.4 millimeter pitch, but we would need to try that in an experimental area.
Okay. And then from Derek, this is probably a common question. What type of other stencil designs on the thermal pads would help reduce voiding?
Tony, you want to answer that, or you want me to?
Yeah, I'll start and please chime in, Greg. So we tested a variety of stencil designs on thermal pads, including different web widths, different areas of coverage, different numbers of bricks, and just generally speaking, higher areas of coverage reduced voiding, fewer webs seem to help reduce reduce voiding. So fewer bricks. So if you have larger bricks with less webs between them, that seem to help. Although without running a web at all, when we printed just a single brick of solder paste on a thermal pad, that had relatively high voiding levels. So you have to break up the print somewhat, but you don't want to break it up too much.
Yeah, I agree. So one of the other papers we've done recently talks about this exactly. And like Tony said, uh, more more bricks, so creating more webs, more apertures on that ground plane created higher voiding than, let's say, just a standard, like if it's a square ground pad, a standard 4 brick pattern with a web in between. The other thing that work showed us was if that web needs to be kind of minimized as far as the width of the web, making that web really thick and pushing those bricks out to the perimeter of the copper area on that thermal created more voids, higher voiding as well. So a thinner web, 4 bricks, brought closer to the center away from the perimeter of the copper pad gave us the best or the lowest amount of voiding percentages in the parts we were looking at.
Yeah, something I'll add to that as well, Greg, you just sparked my memory. When we used extremely wide webs, like say 20 mil wide webs, that's too wide for some solder paste to cover and fill that gap. And we clearly saw voiding forming at the web intersections. That's where they were centered. And so as the web width was reduced, those voids that were intersectional based on the intentional gaps we put into the print, as we reduced the web width, those voids disappeared.
Good. We just got one in from Charles. When adding the toe extender, what method did you use to ensure that the QFN did not lift too high and actually not solder to the pad?
We didn't actually see that.
Well, I'll answer that. Sorry, go ahead, Tony.
In our X-ray images, we didn't see any type of disconnection from that center thermal pad. In all cases, the component was able to settle back down and make contact with that center thermal pad solder mass.
Greg, you want to chime in?
Yeah, I mean, I was gonna say the same thing. I mean, we just looked at up to a 20 mil toe adder and didn't see any reason to think that would happen. I will say, and I saw another question, kind of, has there been other work to support the same findings? When we presented this at Apex earlier in the year, following our presentation, Dr. Norman Armendariz presented a paper, Effective QFN IO Pad Solder Paste Overprint. So it was a very similar project, and he had real-time X-ray video that showed this. He actually overprinted, I believe, up to 40 mils and had video of the reflow process. So very interesting. But the summary of his work also supported that overprinting the IO pads would reduce voids on the thermal pad.
Good. Yeah, I actually was going to bring up that in regards to other studies. I know you guys use a lot of references and reference other data, and obviously you have done a lot of work as well in regards to this topic in particular. So yes, there's plenty of studies out there that agree with what we're working on, and obviously we're always continuing to test and experiment with this. Are there any other questions? Oh, we did just get one. Did you overprint onto masking? If yes, what was the masking height compared to the copper?
Tony, what was that solder mask height?
Solder mask height was typical process. It was between 0.5 mil and 1 mil over the laminate because it was a print and etched board. So we didn't have any signal traces running up to those pads. The pads were just isolated with mask around them. And so the relative height difference was about 0.5 mil to 1 mil.
And to answer your question, yes, we did overprint up onto the solder mask. So we printed, beyond the copper land pad up onto the solder mask, and that you could see from the images we showed in the presentation that the solder paste does pull cleanly back onto those copper pads.
Awesome. Any more questions? Okay. Well, obviously, this is a very popular topic. I just wanted to thank everyone for your attendance and participation today. As stated before, we have recorded this webinar, so it will be available after today. And then obviously, as we continue into this Quarantech Tuesdays, we will be putting out future topics. The next webinar is slated for October 20th and features Greg Smith as we dive into root cause analysis, specifically on the topic of stencil design for SMT component thermallands. So if there's no other questions, I want to thank you and have a wonderful rest of your day. Goodbye.